Welcome to clickmyproject.com. We are going to see the product for architecture of a reusable BIST engine for detection and auto correction of memory failures and for input-output debug validation, link training and power optimization on 14nm SoC. Next we are going to see the abstract for our product. As silicon integration complexity increases with 3D stacking and through silicon via, so does the occurrence of memory and input-output defects and associated test and validation time. This ultimately leads to an overall cost increase. 14nm Intel SoC, a reusable BIST engine called Converged Pattern Generator Checker (CPGC), are architected to detect memory and input-output defects and combined with the software-assisted repair technology to automatically repair memory cell. The memory cell defects on 3D stacked void input-output DRAM. Additionally, we also present the CPGC gate count, power, simulation and silicon results. The reusable CPGC IP is designed to connect to a standard IP interface, which enables a quick turnkey SoC development cycle. Silicon results show CPGC can speed up validation by 5x, improve test time from minutes down to seconds, and decrease debug time by 5x, including root cause of boot failures of the memory interface. CPGC is also used in memory training and initialization, which makes it a critical part of Intel SoC. Shrinking process technology and faster memory bus data continue to drive complexity in the input-output design. The surge in complexity brings with it an increased design bugs. While some of these bugs, such as logic bugs, can be detected at the pre-silicon stage, others such as cross-coupling of adjacent data lanes, voltage through ground bounds, power bounds, timing error due to process shifts, etc. remain undetected. Although logic bugs are possible to detect in pre-silicon with increase in design complexity, shortened design time and complex OS and software demands, this can lead to escalations of bug escapes. A modern microprocessor design can experience considerable design bugs, specifically in memory interfaces. Controllability and observability are key attributes in any post-silicon validation methodology. One conceivable but expensive solution is to probe the prepackaged dynamic random access memory. The easiest and most cost-effective solution is to aim built-in self-test circuitry inside the chip. The BIST engine provides an efficient mechanism to deterministically drive and receive patterns on the memory bus, along with automated data checking capability. These features can be used to swiftly identify and isolate bugs in the silicon validation phase. Furthermore, given the continuous increase in system reliability requirements and the current trend of adding more complex features to achieve lighter reliability goals. Next we are going to see the flow diagram for our product. The typical computer architecture for SoCs consists of one or more processors with a memory subsystem that includes a memory controller and a main memory. Here we are giving the input data along with the memory address to the ROM. In the ROM, the data is stored corresponding to the memory address. The CPGC BIST engine becomes a part of the memory subsystem and the memory controller. The CPGC architecture consists of test pattern generators, defect detectors, a repository of failing addresses, an optional self-repair logic circuit, and configuration register. The CPGC can be programmed through the CR to automatically or manually repair memory defects detected with software. For test pattern generation, we use PRPG. The data we give is 16 bits of length. To 8 bits is multiplied and the output will be 16 bits. And the MASR function process compiles all outputs into one LFSR. Works because LFSR is linear. It obeys superposition principle. Superimpose all responses in one LFSR. Final remainder is XOR sum of remainders of polynomial divisions of each PO by the characteristic polynomial. The comparator compares the data and the memory whenever we give the control signal. The comparator outputs 0 or 1. If the data and the memory is matched, then the output will be 0 because of no errors. If the data and the memory is not matched, then the output will be 1, indicates error. Finally, we are going to see the output for our product. Double click on the BIST project icon. We use Xilinx 14.2 version. Here we have to create the new project and save the new source into that project. The file consists of the main code. Then for the output we have to click on simulation, main, and then simulate behavior model. Once we simulate, the simulation will run in iSim. Here the control signals are reset and clock. We have to give the value for the reset. The reset initial value is 1. Then for clock, click on force clock, and then leading edge value is 0 and trailing edge value is 1. Period is 1000 nanoseconds. Then we have to run. Again for the final output we have to force constant value as 0 for reset. Then we have to click on run button. The address is indicated here and the data is indicated here. Then again click on run. The address will be in 3 bits and the data is 16 bits. Again click. So the data corresponding to the memory has no errors. This time the error has occurred, so the output FDS becomes 1. For pressing the run button again and again, the output 1 remains unchanged because of error. Again we have to reset. For reset give 1 and then enter, then again run. It will be reset. Then force constant and 0, then run. Here the memory and data will be matched, so the output is 0 because of no error. Then we have to see the RTL diagram and synthesis report. For RTL diagram and for synthesis report we have to click on implementation, then implement design. Here the synthesis report is generated. Here the number of flip-flops used will be given and LUT. Then for the timing report we have to click on timing report. So here the timing will be given 2.336 nanoseconds. For RTL diagram we have to click on view RTL schematic, then main, add, create schematic. We have to double click on this. The architecture will be created. Thank you.